Okay, so we are saying that the previous class we worked on a code and it was not blinking. You are saying, but here in my board it was working anyway. Let us go through the
So it
blink.
was working fine. I also tried it.
Hmm.
It was
Okay.
working fine.
Still we can go through some more concepts which will be helpful. So I believe you recall that first of all, to make any LED or any GPIO port on or off or make it high or low, first of all we need to know the base address, and then we also need to know the offset address. And there are certain registers which are very important to understand whether that particular GPIO will work as a digital input or not, or whether that particular GPIO pin will work as any alternate function or not. Okay. So first of all, in any case, we must know that GPIO's base address. So GPIO, I discussed the block diagram of the microcontroller, and you might have noticed that there are two different types of bus which are available, which is actually one bus family is APB and the other bus family is AHB. Okay, and their base addresses differ with respect to the bus. Okay, so GPIO A, the base address if you are using APB is 4000 4000. If you are using port B in APB, then it is 4000 5000, and similarly 4000 6000 7000, and so on. Okay. I, so now the question is, these two buses, okay, are not available for every peripheral. You must check beforehand whether these buses are available for all the different peripherals or not, or whichever peripheral you are going to use, you must first check whether that peripheral is supported by this bus or not. For that for that you can just go and check the architecture or the bus diagram or bus matrix of the microcontroller. So AHB, of course, it is high performance bus, is much faster than APB, which is, you can say, the conventional or legacy bus. So this bus was available from the past. Okay, so or the ARM was using this bus in the very beginning. It started with this APB bus, and later, with respect to development and all, they introduced AHB. So to provide backward compatibility, they kept these two buses available in all the future microcontrollers. So what is the advantage? AHB allows one clock cycle access to peripheral. This is one very big advantage. That means in one clock cycle itself, you can access any peripheral provided the AHB must be there with that particular peripheral. APB is a bit slower and it requires minimum, okay, two clock cycles. So of course AHB is much faster. But like I said before using any GPIO, we must enable that particular module's clock. Okay, and we have studied about RCGC GPIO. RCGC GPIO, which actually provides the clock to that particular GPIO bus. So if you are interested in port F, okay, then you must enable the clock of that particular GPIO using this particular register RCGC GPIO. And we have used RCGC GPIO to configure the port F. Now coming to arrays and pointers, and how can we use arrays and pointers to use the features of different registers. First of all, arrays, we remember arrays are collection of, or they are a set of common data type variables, okay, or a variable which are having common data type. So these are set of set of variables which have the same data type, like var1, var2, var3, and so on, var n. And all these variables must be from the same data type family, okay. So they all should be from same data type, okay. So this is one important mandatory rule for the array. And apart from that, all these variables are indexed, okay. So 0, 1, so these are all indexed, 2, and so on, okay, and -1. So these are all indexed. Third, all these variables are arranged in consecutive memory addresses. So they are allotted consecutive memory addresses. So if we can remember these three properties of an array, then of course we can correlate the concept of array with the registers that we are going to access, and we can use pointers. When we are talking about pointers, of course pointers will point to an address, okay. They can point to an address, and of course you can use pointers and then dereference them for changing the value of that particular variable. So all these array elements are having some addresses. We can point to that address using a pointer or attaching a pointer to that address, and then rather than changing the variable directly, we can use pointers to change the content of that particular memory location. So this is what we are going to study today. And of course you can correlate the concept of arrays and pointers in C with the registers which are available in the microcontroller. So let us see.
Sir,
Mhm.
the screen sharing stopped.
Okay. Whenever the screen sharing stops, now just please let me know, because this is having some issue. I think there is some issue in the internet of our institute. Okay, so I hope the screen is visible now.
Yes, sir.
Okay, so any moment the screen sharing is stopped, let me know, because I cannot cross check what is happening in the background. Okay, so what are the things that we can note? We can note that we are talking about ports. When we are talking about ports, we know that port A, B, C, D, E, F. These are the ports which are available with the microcontroller or Cortex M4. Each port can have 8 different bits. So D0 to D7. Similarly for your port B, D0 to D7, and similarly for port F, D0 to D7. So that means, not sorry, I'm not sure whether they have D0 to D7. All the pins are not available with port E and F. Okay, port E and F do not have all the pins from D0 to D7, because in total there are 43 pins available for us. Okay, and here we have 6 ports, so 6, it's a 48. But actually it is not 48 pins which are available for us. 5 are not available with port E and F. Rest A, B, C, D, they all have 8 lines. Now using 8 different lines, okay, So if port A is having 8 bits, so 8 bits means we can have 2 to the power 8, 256 different combinations which can be generated at each port. So suppose we are talking about port A. Okay, so port A will have D7, D6 up to D0. So how many different combinations can we generate at these ports? Of course, we can generate combinations from 0, 0, 0, 0, 0, 0, 0 to, okay, 1, 1, 1, 1, 1, 1, 1, 1. So these are all different possibilities which we can generate. And if you count, it is 256. Of course, 0 to 256, 2 to the power 8. So using 8 bits of any port, we can generate 256 different combinations. And remember, we have discussed in the past also that these ports allow changing a single bit also. It is not necessary that I always have to throw all the 8 bits in that particular port. We can change even a single bit without disturbing any of the other bits. What do you mean? What I mean by that? For example, D6, D5, D4, D3, D2, D1, D0. If I am interested in only changing this bit at D4, okay, be it 0 or 1, I can change it without disturbing any other bits. And this was actually, we noticed this kind of behavior when we were using bitwise, bitwise, bitwise logical operations. Okay, we have checked this behavior when we were using bitwise addition, bitwise ANDing, bitwise ORing, bitwise masking and all. So this is available with the ARM Cortex. So you don't have to always throw all the 8 bits simultaneously to change the behavior of the ports. We can even change a single bit by changing one of the bits of interest. Okay. So there are 256 combinations which can be generated. Just a second. Okay. So coming to port F, let us go to the data sheet if possible, so that we can keep an eye on what we are saying. So port E, sorry, okay, and then we have, by the time you can also open the data sheet. Okay, let me check. Is that the, yeah? So here, suppose we are interested in port F. So first we will go to GPIO port, okay, GPIOs, and then the register map. Here in the register map, we can see GPIO port F. Okay, here GPIO port F is having 4002 5000. This is the base address, right? Then apart from that, these are all the registers which are available with every port, be it port A, be it port B or port F. Okay, so these are the all the registers which are available for different tasks. Okay, for example, data register to change the port's value, direction register to set it input or output. For controlling the interrupt and sensing the interrupt, we can use these pins and so on. So here, when we are talking about the port F, this is the common address for port F. What do you mean by that? It means if you see 4002, this was the base address, 4002, then 5000 was the base address, right? And if you see here, the offsets, they are all of 3 bits, 3 digits, 000, 400, 404, and so on. So only last 3 digits are changing. Rest 40025, this is common. So this particular number is common, right? For port F, common for port F, for port F, right? So this is common, and rest three are changing. These are all offsets, and these are all changing. Now, so first of all, we have to understand 40025 is common for port F. Rest of the 10 bits, okay, if you check now how rest of the 10 bits, why we are talking about 10 bits, I will come to that. So here we have 3 bits or 3 digits left, okay. So 3 digits means if you are saying 0, then it should be 0000, 0000, 0000, right? So because each one digit is represented by 4 digits or 4 bits, so because it is an hexadecimal value. So out of these 12 bits, okay, because remember these are all 12 bits, 12 bits. Out of these 12 bits, 10 bits are used to generate these 256 combinations. Which 256 combinations? Because 8 bits are allowed for changing the values. So why only 10 bits are allowed? We will come to that. But remember, these 10 bits, okay, so these 10 bits are used to generate all the 256 combinations. Rest a0 and a1, because these two, okay, are a0 and a1, okay, these two bits are not used for generating any of the 256 combinations. Why? Anyone? Why last two digits are not disturbed in this case? Why last two digits are not disturbed? Okay. Anyone? Why only these out of, for example, it is very clear. This is common. 402.5, 4025. This is common. It is clear, I believe. Right? Rest three digits are used for changing the bits. And we know that each port can have 8 bits. So that means 256 different combinations can be generated at that particular port. So to generate 256 combinations, we are not using 12 bits. We are only using 10 bits. Rest, the last or the LSB or the two last bits are not used. Why? These two bits are not used. Why? Anyone? Can you correlate this concept with some of the concepts which were told or discussed in the very beginning of the courses? Can you correlate why these two bits are not used? Or while managing the memory, the cortex M4 or cortex generally do not change the last two bits. These two bits are not used to 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 allot any memory. Why?
So because
Anyone?
little India,
Little endian actually is nothing but the way to read the number, whether you are keeping the MSB first in the reading or LSB first in the reading. But I am talking about why last two bits are not used. Anyone remember this particular concept? Alignment of memory. Anyone? Alignment of memory. We discussed about alignment of memory. That means byte wise alignment, half word wise alignment, and full word alignment. Anyone remember this concept? Why we do not use the last two bits? And when we use word alignment, we always end up with the memories where you have 0, 4, 8, and C. You remember or not? Half word alignment 0, 2, 4, 6, 8, A, and C, and F. Okay, and then here byte-wise alignment, you can use any one, 0, 1, 2, and so on. Remember alignment of memory?
Yes, sir.
When we are using 32-bit system and when we are using ARM based 32-bit system, they always avoid last two bits to generate or to allot the memory for full words. So remember, because we are using that kind of alignment approach, or the ARM is using alignment approach, last two bits are not used to generate any pattern. So that's why out of 12 bits, only 10 bits are used, and rest of the 2 bits, A1 and A0, are not used because, of course, the ARM always try to manage that alignment of memory. So whatever combination you want to generate, you can generate by changing these 10 bits. Okay, but leaving the rest of the 2 bits. So remember this. First of all, port F has this common address. Okay, and the rest of the three digit means 12 bits. Out of those 12 bits, 10 bits are used. Rest A1 and A0 are not used to generate 256 combinations. Okay, so if I go, just keep an eye on that. In that case, what we can learn from here? Okay, we can learn something like this. We have 32 bits, right? We have 32 bit register. Each register is 32 bit. So if I keep on addressing, so this 4 1, okay, then you have this 4 2, then you have 0 0 3, and then 0 0 0 0 4. Okay, so this is how the system actually works. So now you have 4, 8, 12, 16, and you can go on adding 0 up to 32 bits. Okay, in that case, if you read now, so this combination 0011 is 3, 1111 is F, and then 1100 is C. So what does that mean? It means all the combinations can be generated by using 3FC in the port F. Okay, I will make it more clear. For example, here we have A0 to A9, which is represented here also A9, A8, A7 up to A0. So A0 to A9. So these are the address lines coming to the port of CPU. Okay, so therefore 32 lines are coming. Each register will have 32 lines. These 32 lines are coming. I am only showing the 10 lines out of 32 lines. Assume the rest of the 32 lines are also there. But our interest is on these particular lines. So 1 1 1 1 1 1 1, okay, up to A2 to A9. We can keep 1 1 1 1, and then remember these two bits A0 and A1 are not used for alignment purpose. So these two are not used. So they are kept 0 0. Okay. So rest, if you introduce from 0 0, and then if you put 1 1 1 1, this is the maximum address. So 0 0 1 1 is 3. Then you have 1 1 1 1 F, and then you have 1 1 0 0 C. So 3FC is the offset, okay, which you can use to generate different combinations at port F. So the address can go up to 4000, 4002, 5, 3, FC, because 3FC is coming from here. Okay, let me make it more clear a bit more. Okay, let me show you another slide. We will come to this. Okay, for example, now it will be much more clearer. So base address of port F, if suppose someone asks you, so 4 0 0 2, okay, 5 0 0 0. So base address of port F is this one. How can we know that? Just go to the data sheet and check the base address. So you can see here the base address of port F is 4002 5000 if you are using APB. If you are using AHB, then in that case 4005D000. Okay, we are using APB right now. So therefore 4000 to 5000. This is our base address. So this is here base address 4000 to 5000. Now this is here we can see all the 32 bits from 0 to 31. So all 32 bits are there. Okay. And we know that 4 0 0 2 5, these 5 digits are common for port F, and rest of the 3 digits will be used to generate all different combinations. But remember, due to address alignment, last two bits are not used, so they are kept 0 0. Okay, 0 0, and rest from, because 8 bits are there in each port, remember. So 1 2 3 4 5 6 7 8. So these 8 bits can range from 0000 to 1111. Okay, so if you assume you are going for 1111, then in that case this will become 0 0, because these two are not in the 8 bits. So 0 0, and then 1 1 1 1 1 1 1 1. Now if you read these 3 digits, it will be 3FC. So in this way, now you can generate all possible combinations by changing here from digit number 9 to digit number 2. Okay, you can put any number 0 0 0 0 0, or you can change 1 1 1 1, or any other combination between this 9 to 2. Okay, so these addresses are allowed for you. So maximum that you can generate is 4 0 0 2 5 3 FC. Okay, so in this way you can change the pattern of the LED, LED or any device which is connected to port F. Okay, so leaving that part, I hope it is clear now why we are using 3FC, and rest of the out of 10 bits. Okay, we are not using all the 10 bits, only 8 bits are required, because any port A B C D E F, they will have 8 bits. So 8 bits are here, and rest of the last two LSB bits are not used because for address alignment, so they will be always 0 0, and rest you can introduce from 0 0 0 0. So the base address is 4025, which is common. Then you can have maximum 3FC, which can be used to generate any particular pattern or any particular number on these 8 lines. Okay, so there are three different approaches by which we can make that any particular pin, or assume LED. Assume we have connected LEDs to these pins. So to change any particular LED or make any pin high or low, we can use three different approaches. One is this approach, which we have discussed in the previous class, by using here, okay, dereferencing plus typecasting. So this is the address, base address 4002 5000, and then after the base address you can go to a particular offset by using this approach also. which is shifting of bits. What does that mean, shifting of bit? So we know this particular sign is left shift, left shifting. Okay, left shifting. And this particular command is very helpful when you want to change only one bit of any particular sequence or any particular register. Okay, so what does this particular command tells you? It means you are introducing one at the second place of that particular register by left shifting the one. So suppose you have, assume we have an 8-bit number like 0 0 0 0 0 0 0 0, and we say we want to move one in this particular place. In this particular place we have to introduce one. So it is not necessary that we always use this particular whole number 0 0 0 0 0 1 0 0. You in that case you will say okay, it will be 0 4. So we will write 0 4 in this particular register, which will be 0 4. Okay, it is not necessary that you always use 0 4 in that particular register. Rather, you are interested to bring one in the third place from the left. So you can use this kind of command and you can just say whichever register is this one. Okay, you can just use this particular left shift. Okay, 3. What does that mean? So first place, second place, third place, automatically in the third place you will have 1. Okay, so this will help you. Why? Because when you are dealing with 8 bits, you can write okay 0 4 or any other number. But when you are using 32-bit register, it won't be that easy to, okay, suppose I say introduce 1 in the 19th position. 19th position. Okay, introduce 1 in the 19th position. It will be very difficult for anyone. For example, we have a 32-bit system. So D31, D30, and so on. And here you have D19, and then you have D0. Okay, so D19 means 20th position. So suppose I want only one here, and rest of the bits should be 0 0 0 0. Okay, 0 0 0 0 and so on. Now one way is to decode this particular number in hexadecimal and write it on that particular register, which will be very time taking. Or you can use simply this particular left shift command. Okay, and tell that you are going to introduce 1 in the 20th position. That's all. So that this means you will introduce 1 in this particular 20th position. So it is much easier rather than decoding okay what is the number and how to put that number in that particular register. Simply go to that 19th position or 20th position and write that 1 there. That's all. So this is bitwise manipulation. So bitwise manipulation, we can use left shift. Okay, left shift operation to introduce 1 in a particular position of the register. Okay, we will use more often this approach or this technique to make an LED 1 or 0. Okay, rather than using the whole number like 0 4 or something like that. So avoid that approach because it is very time taking. We can use this particular approach where you can just directly tell introduce 1 in the second position of the LED of the register, sorry. Otherwise now this particular segment is also very difficult to read because always you have to go to this particular register. For that you will write the whole lengthy program or the whole lengthy code and then you introduce something. Don't have to do that. What we can do is we can use the macros. Okay, and we can just replace this whole line from here to here, okay, using a macro like star GPIO F data bit register or whatever register you want to call that. Okay, so this is another approach. And simply last but not the least, most simple approach is to use the whole macro, and then in the array you can specify, because remember here all the memories which you are dealing with, these all memory you can see they are always aligned in a particular memory, and they are always consecutive. For example, 400, 404, 408, 400C. Then after that, 410, 14, 8, 18C, 20, then 500. And here you can see there is a gap 420 to 500. Okay. So this is not just 32-bit registers gap. This is a big gap. But even after that, the memory started from 500, 504, 508, 500C. So indirectly you can see 048C, 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 and so on. Because always the system or the ARM tries to align the memory according to word size. So word size alignment. So therefore you have 048C. Okay. So now we can easily see that these are arranged in the memory, which are basically nothing but arranged in an array, because all these data are of same data type. Okay. Secondly, they are arranged in the consecutive memory addresses. So we can use arrays to enter some value in that particular position. So we can use arrays to change the value in that particular register. Let us see what does that mean. So using all these three concepts, we can simplify our approach for coding step by step. Okay. So first of all, let us check how to get into that particular register and then change the value of register using three different approaches. Okay. So here you might be recalling there are three LEDs available in the microcontroller board, which are connected to the bit position 1, 2, and 3. Okay, so red, blue, and green. So these three LEDs are inbuilt in the microcontroller board. Okay, remember this is port PF1, PF2, PF3. Okay, I hope you remember this particular 3 bits position, and these two are switches, PF0 and PF4 are switches. Okay, these are all switches, switch number, switch. These are the two switches, user switches. Right now we are interested in the LEDs because we are just going to make them high or low. So just note this: PF1 is red, PF2 is blue, PF3 is green. So what is the bit position? So this is the first position, this is the second position. So if I want to make, or if I want to make 1 in this position, I will just use this code. Move 1, 2 positions left. If I want to come to this P2, okay, this particular line, then in that case it will be just 3, and similarly 1. Okay. So let us keep an eye on that and check these things. Okay. So sorry, this is 0, this is 1, 2, 3. Okay. So 1, 2. Okay. Let us look into the program. Here what we are doing, we are defining. Right now I don't need the header file. I will just keep the header file off. Okay. Let us see here. Define. This is a macro to define any name. So LED red is a meaningful name. And what does that mean? LED red will be signifying this command. So instead of using this command again and again, I'll be just calling LED red. And what is this command going to do? It is going to introduce one U in the first position of the register. So first position here, okay, first position P1. Second position blue, third position is green. So if you need to introduce one in the second position, then you will use this name LED blue. It is your choice. Okay, you can just call L blue or any name, or even LB. It is your choice. Then define LED green, which is moving one U. One U here it says one U means unsigned one in the third position. You should read it like this: unsigned one in the first position, unsigned one in the second position, unsigned one in the third position. Or you can just put a comment here: unsigned one in the first position. Okay, so this way you can just read it, because first few times it will take to practice to understand what this particular code is doing, but it is very easy to understand after 2 or 3 iterations. So third position means in the third bit position. Okay, so it will be the green LED if you want to make it on. Okay, now this particular thing is coming from the header file. Okay, in the previous class we have used the memory address like this: unsigned, long, volatile. Why we are volatile we have discussed in the previous class. If the software is using optimization level, high optimization level, then it may remove the unwanted variables from the program. So therefore, to avoid such removal of variables, we should always use volatile in case we actually want that variable to be present in our code during the runtime. Otherwise, sometimes due to optimization, the software, the IDE may remove that particular variable. So one approach is this one: unsigned, long, volatile. Let me make it big. This approach, okay, and then use the base address plus the offset. Okay, you are shifting it to 2 positions left. So avoid these techniques, or to avoid this particular approach, we can use the header file. And let me introduce the header file to you, and I will share it with the class also. Okay, so what is there in the header file and how the header file is basically written, and then where we can get this header file, who provides this header file, and how the header file actually helps us to simplify the program. So first of all, let us go through the header file. So here is the header file. How we can add the header file? For timing I can remove it. Okay, remove the header file. So if you want to add the header file, you will right click on the project, add files. Okay, and then in that folder wherever you are running, or you are keeping the main file, keep the header file there and open it. That's all. So in the header file, let us go through the header file first. Okay, in the header file, what are there? In the header file, it says if and if, then it declares something, and then it defines the name of that particular header file. I have discussed about this particular macro also during one of the classes when we were talking about preprocessors and macros. Someone asked me what is if and def and all. Okay, if and def. If not defined. Okay, how to read this particular line? If not defined, what is not defined? This TM4C123GXL dot H. Okay, so here we have two underscores, underscore underscore. This is how we define the header file. Okay, so if not defined, underscore underscore the name, whichever name you want. Okay, instead of dot we are using underscore here, then H, this is representing that it is a header file, and then underscore underscore. If not defined, if tm4c123gxl.h is not defined, if this particular macro is not defined, then in that case define underscore underscore tm4c123gxl dot, instead of dot you are using underscore h underscore underscore. What does that mean? It sometimes it may happen that you are using a header file or a function which is also defined somewhere else in the program. Okay, so if multiple definitions of any particular function is there in the C program, then there can be a conflict. To avoid that, we should write or we should use this particular line. That means if it is not defined, then define it like this. Okay, and because it is a header file, so first of all we are defining the header file name. So tm4c123gxl dot h under. Okay, and if you come here, because if you remember, if we are using if, then we should always end up the if also. So and if. Okay, and if is also there. So if it is not defined, then define, and then and if. Leave it. Okay, this part. Okay, then what is there in the header file? You can now notice something which is very common throughout the header file, like this. Hash define. Hash define is the macro. What you are defining? A variable name for the register, and this is the address of that register using pointers and typecasting. Okay, so you can use rather than writing this same line again and again. Which line? This line, star unsigned long volatile star, then the address. Okay, this is defined here in the hand. Okay, previously. So you can see here port F. Let us come to port F. Let me divide this window in two vertical. Okay, please try to understand. If you have any doubt, you can ask. Okay, so here we have this particular line which is written for the port F. So let us go to the port F here. If I can keep floating. No, no, it is not possible. Okay, let me go down to port F. Port F. Port E, port F. Okay, so we have used port F. So this is the base address of port F, if you can recall, 4002, 5000. So see here what is written for that. Okay, so define GPIO port F data register. Then they are specifying the address of that particular data register. So here you see 400253FC. This is what we were discussing here, 53FC. So 400253FC is the address of port data register. This one, data register. Okay. Similarly, if you come down for the direction register, DIR. So this is the DIR register. What is the address for DIR register? star volatile unsigned long. Okay, volatile you can keep here, or you can keep after the variable declaration also, like unsigned long volatile also. So it is your choice. So volatile unsigned long, then you can see the address 4002 5400. So this is the address for dir register. Let us check in the data sheet. dir register, okay, here. So what is the base address? 4000 to 5000 plus 400, right? So let us check here. So let me just window. This is okay. Let me go to port F. Okay, this will help you to write your own data, uh, to write your own driver file in future. Okay. So here you can see port F dir. So port F dir, and this is the address 40025400. So 4025 is common, 400 is the offset. So what is the complete address? Complete address is 40025400 for the dir register. Yes, dir register. Let us go through rest of the registers just for a glance. Okay. Then we have GPIO IS. Here they are calling it IS underscore R. The R is representing that it is a register. Simple. Then you have GPIO IBE, GPIO IBE, GPIO IEV, GPIO IEV, then IMR, so IM, then RIS. So here you can see RIS and so on. So you come down, and the last is GPIO cell ID D3. Okay, this is all about that. So this is how all the registers are arranged in the memory, and this is how the header file first lists all the available registers in the microcontroller. So you have port F, port A, port B, and every register. So where they are getting this all these registers, basically they are getting from the data sheet, because we are looking at the port. Rather than that, you can go in the very beginning and check the register map of the whole system. So whole system has its own register map, and this is actually mapped in the header file, okay, in a sequential manner. So this is one approach of writing the header file, and you can see the header file runs down to 10,026 lines, and you don't have to write it because this is provided by the company. How can I get it from the company? You can go to, for example, we are going to use microcontroller from Texas Instruments, so you can directly go to uh, PM4C123GH6PM. Okay, and then you can write mm, driver, peripheral driver. Okay, done. So you can come to this particular link, and then you can get the header file from here. Okay, this one TM4C123 Tiva where C series software, and you can get it from there. Anyway, you don't have to worry about that. I will provide you the header file in the classroom. I will share the header file. Okay. So this is one approach of writing the header file. So this is a very, what to say, basic approach of writing a header file. Okay. So what we have learned from this lecture, what we have learned is, first of all, we can access the register by using this pointer and dereferencing the pointer. Apart from that, we can use the header file. The header file contains the list of all the registers which are available in the microcontroller. Now, how to use or how to utilize these registers which are there in the header file? Okay, for that you just have to come here in the main program. Okay, and first of all you need to know, okay, where is RCGC GPIO? So go to header file, Control F. Okay, and you just type RCGC GPIO. Okay, so here you got the RCGC GPIO. Just copy this one, sysctl RCGC GPIO underscore R, copy, come here, paste. So this is the dereferenced address of that particular register. And now we are using or equal to. Or equal to means you are using the masking approach using or technique. For what? If you want to just make the which pin you want to make, high or low, for that we have studied for making port F. Okay, to provide the clock for port F, we need to provide the clock to the pin number 5. So to go to the bit number 5, you can use this command, which is directly 1U left shift 5 positions, and this means we have entered 1 in the 5th position of the GPIO RCGC GPIO register. Okay, and if not, you can directly go to this particular address and then check RCGC GPIO. Okay, so this is the register and page number 340. I will go to page number 340 directly. 340. So this is my RCGC GPIO. And here it says, if you want to use port F, then you have to provide 1 on the R5. R5 is here, 5th bit position. Okay, so R5, if you want to make the port F, provide the clock to port F, to activate the port F, make 1 at R5, and that will enable and provide the clock to GPIO of port F. Simple. So this is how you can just use the or equal to function, or you can read it like this. This is read like this. So uh, sysctl GPIO r is equal to this plus, okay, or sorry, not this plus, or 5. That means 5th position. So 0 5. Okay, 5th position, I have to note it down. That is, this becomes complicated. Okay, so anyway, so you can just pick 5th bit position. So this is how you can read the whole instruction. So using bitwise ORing, you can just make one of the bits high or low. So this is how you are making that particular bit high. So this command will produce, or this command will generate clock in the port F. Anyone having any difficulty to get to this point? That
No, sir.
how you reach to the data sheet, first thing. Okay, and in the data sheet, this is nothing but an arrangement of all the registers available in the microcontroller, and this command we have learned from the previous lecture, how to use pointers and dereference the pointer. We have learned it in the last class. We also learned how to make our own name, or how to give our own name, and previously we used some other name like RCGC GPIO. Rather, the data sheet is providing you all the details, so just have to come to the the header file and just type RCGC GPIO. Okay, and you will get all the details. So use this particular register, copy, paste it here, and because we have to make the 5th bit position 1 for to activate the clock in the port F, This is the command. By this command, you are entering 1 in the fifth position or R5 position. Okay, bit position 5. Okay, now, and then we used different command to reach to the dir register. Okay, in that instead of that, you can directly come to the data sheet, control F. You can just write port F. Okay, sorry, control Z. Here, this is the arrow for next. Okay, next. So by next, you first reach to the port F. So this is all, these are all the list of registers which are available with port F. So here you have the direction register. So this is the name for the direction register. Copy this, control C, come here, control V. So this is the data direction register, or equal to, again, why? Because we are just trying to make one of the bits high, okay, without disturbing any other bits. Okay, or equal to. Now, in the bracket, what we are doing? LED red, LED blue, LED green, and all three are odd. What does that mean? It means we are entering one, okay, one U in the first position, second position, and third position. Okay, so you just write here LED red, okay, or LED underscore blue, sorry, blue, and or LED underscore green. Done. So this is how we are using bitwise or operating, or you can say masking operation using or, and we are enabling all three LEDs. Simple. So all three LEDs are now, or that positions, bit positions are now output, because dir register tells the direction whether it is going to be an input or output. So we have defined it output here. Delete. Okay, so this is done. Then after that, dir register is done. Similarly, you can use den register, data or digital enable register, and you are making all three pins digitally enabled. And then what you are doing here in this line, in the data bit register, okay, in the data bit register, you are making LED blue. So right now you are making only the third bit high. Okay, this is how you are using the array to reach to that position and making the LED high. And then you are using the while operation to make the blinking on or off. Okay, and this we did in the previous class, the same thing, int volatile counter. Okay, and we are using that counter function, and rather than using counter again and again, we are using counter as an array, which, you know, 0 0 and 0 1. So it is not that important, because this is the different approach to make the while loop. Okay, so rest.
Sir,
Hmm.
so for digital enable, we won't use the OR operation.
You can. Where is digital enable? This one.
16 line, yes, sir.
This one. No, you can use. You must this one. Yeah, or equal to. No issues.
Okay.
Or equal to means it just make sure that you have made all these three bits position high. Okay, so whatever be the other bits position, it does not disturb rest of the bit position. It only will make these three bit positions, which are the bit position 1 2 and 3, high. Rest might be possible, rest of the bits are having some other values like zeros or ones, but we don't want to disturb them. Just we want to make these three bits high. And I told you about bitwise ORing. Bitwise ORing means whenever we want to deliberately make one. Bitwise ANDing we will use when we deliberately want to make zero without disturbing rest of the bit positions. These are all bitwise ORing. So we will not be disturbing any other bit positions. Okay, so now you are making the LED high, red LED high, and then LED low. Okay, so here you have made the blue LED high. Okay, and then you are making the red LED high low high low high low. So by default, what kind of effect you can expect from this program? This program will keep the blue LED always high, and the LED red LED will be blinking high low high low high low and so on. Okay, so let me just try this. If I can load this into my board, and if possible I will try to show you this program. Okay, uh, for that let me just connect my camera if possible. I am not sure, but let me try.
So can you explain that line once in which we are assigning the LED?
Just a second. Mm, just give me a second. IV cam. Hmm. Which one? Which line?
So in which, for example, line number 25.
Hmm. 25. This one. GPIO port LED red.
Yes, sir. Because here we are not using that 3FC thing. So how is it assigning?
Okay. GPIO port of data bit R. This is one array. It is clear. Okay. This is an array of registers, right?
Yes, sir.
Okay. So this is an array. In that array, what you are passing in this array, LED red means 2.
So this array is that thing which has offset 000, right?
Wait a second. Let me just show you the data register. Okay. Here you have the data register. Okay. Here you have the data register. This is the address of the data register which we have decoded. Okay. By default, the base address is this one. Let us go to that register, data register. Okay. So for that, I'll have to go to GPIO data. If I can find, otherwise I will use the GPIO register map. Okay, coming down to then, because it is the first register, it is not that difficult to get to that register. Okay, so this is the GPIO data register. Clear?
Yes.
Coming down here, this was all about that 9 is to 2. That means only 9 to 2 numbers are used, rest of the bits are not used and all, right? So now if you read this particular register, what it says: GPIO data register is the data register. In software control mode, values written in the register are transferred into the GPIO port pins if respective pin have been configured as output through GPIO data register, direction register. So we have previously done this part. So DPIO direction register, we have told this the program that it is going to become an output register, right here. Clear? These 3-bit positions are output. Now, coming to the data register. In the data register, we have 0 to 8 in our hand, right? 0 to 8. So, what is this 0 to 8 or 0 to 7 going to do? This will be the GPIO data. So, 31 to 8 are reserved, so we will not be using it simply. This is not going to be used. Now, coming to 7 to 0. This register is virtually mapped to 256 locations of address space. 256 locations. Why it is 256 locations? Why it is not saying 256 different combinations? Why 256 locations?
So because only 10 bits are used,
No, 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 no,
out
no,
of which,
no, no, no. 8 bits are used in every port. Please try to focus. Okay, 8 bits are used in each port, right? D0 to D7. But which 8 bits? Those 8 bits are from 9 to 2 of the address register. So why 256 locations? If you can remember bit banding, we have talked about bit banding in the past. Have you Do you recall what is bit banding? In the past we discussed one topic called bit banding. What does that technique, or what is this significance of this particular technique in ARM? Look, bit banding says each bit, each bit in the bit banded bit banded registers have a separate address. If you can recall it, that means each bit has its own address. So that means if you are saying 256 different combinations, then there will be a bit banded 256 address locations. Anyway, if you cannot correlate, leave it. Okay, don't worry. So here let us go through the data sheet. It says the register is virtually mapped to 256 locations in the address space to facilitate reading and writing of data. These registers by independent drivers, the data read from and written to the register are masked by 8 address lines, which are 9 to 2, which I have showed you here. Why 9 to 2? Okay, rest A0 A1 are not used, so this is A9 to A2. Okay, this is in case of GPIO data only. Now this register reads from the data. This register returns current state. So if you are trying to read it, it will tell you what is the current state. And if you write to this register, only affects bit that are not masked by 9 to 2. So you can only write on these registers or bit positions which are between 2 to 9, which are here A2 to A9. Okay, so you can only change these locations. Okay, as an output. Okay, so here now 0 to 7, though you will be writing on these registers, okay, to make any particular bit high or low. So first of all, if you are interested in port F, then this position here, wait, let me just comment. This is your red LED, this is your blue or green,
Green. Green.
green blue LED, and this is your green LED. Okay, so these three LEDs are there. So if you want to make this particular bit 1, make it left shift 1, left shift 2 to make it blue, and then left shift to green, third position to make it green. Now coming to the code, this particular line, so GPIO data bits register, and then you have the array. Okay, in that array you can use this particular approach also, there is no harm in that. Okay, you can use all three different approaches. These are all allowed, you don't have to worry about that. So what you are saying here, in the position number 2, why position number, sorry, 1, position number 1, because LED 1. So this particular position, make it 1. Matlab, that means you are saying on that particular register, which register? GPIO register, at this position which is indexed with, what is the index? 1. You got the index position 1,
Yes, sir.
and what you are entering in that at index position 1, so you are making
One
it high.
zero. So we are entering 1 0, right?
1
Because
0. Why you are using 1 0 here?
because one is at the first position, if we are shifting, so it becomes 1 0.
This particular instruction will only make the bit position once 1, that's all. That means here If you see here, if you want to make one here, okay, in this, sorry, control that, in this position, if you want to make one, if you want to make one here, okay, this is what you are saying, left shift to 1. It does not mean 1 0. You are not changing two bits, only one bit you are changing. You got my point or not?
Yes, sir.
When you are passing this command here, one u to left one position, okay, in that case you are only changing one bit. These are all bitwise manipulation. When we say bitwise left shift, bitwise oring, bitwise anding, that means only that bit will be changing, rest of the bits do not change. You got it or not?
Yes, I got it.
So when I am saying here only one bit is moved, so it does not mean that it does not mean that first it will be one here, then that one will be moved here. No, it is not like that. Remember, okay? It just means you just entered one in this position only. Okay, or in short, you can just read it like this, that move one, but because one u, when I'm saying one u, especially because so that you don't get confused, so one u means one u unsigned one in the first position, unsigned one in the second position, unsigned one in the third position. So unsigned one in the first position, unsigned one in the second position, unsigned one in the third position. And you should not read it like when we are saying third position means 1 0 0 0. This is not correct, because in that case you are saying you are changing 4 bits. This is not. You are not changing 4 bits. You are changing only one bit. Understood?
Yes, sir.
Directly coming to the third bit position and making it 1. You do not change it like this, okay, first you will have 1 here, then it will come here, then come here, then come here. No. So in that way you will be manipulating 3 or 4 bits to reach to third position, which is not allowed. This is not the case. The case is come to this position and make it 1. Okay. So similarly, now here what you are reading, this is an array. GPIO data bit register is an array. In that, go to which index position? First index position. Why? LED 1 is 1. So go to the first index position and make it 1.
Sir, if you
Okay.
would have written one in place of the right LED underscore red, then also it should have worked, right?
Where right LED?
In
Where is
that
right?
in that line only, in the right side.
Which? This one.
Yes, sir. If would have written one, then it would have worked.
Yeah, you can. One U, you can just write one U.
Yeah,
No,
then
here
it would.
it will not be one U, it will be 02. Wait, it will be
Yeah,
02
sir. Yeah, sir.
because,
Yeah, yeah,
got
sir.
it?
Good,
It is
good. Yeah.
0x02U. You can write it like this, no issues. We did it in the past class, we did the same thing in the last class.
Oh,
02U, why we are saying 02? Because it means uh, like this, it can be 00000010. Now you can see it is red LED here, right? Got it?
yes, sir.
So rather than using such an approach to go to 2 or 4 or 8, because tomorrow, if suppose, like I said, if you want to make the D19th position or D18th position 1, then how you are going to calculate this number? So rather you just directly use this particular approach. One U in the 19th position, one U in the 20th position, or whichever position you like. Okay. So in this way we can make the LED glow. And let me check if my camera is working or not, and then we will see. Okay, let me check. So here, mm, my camera is Let me just change the camera. Yeah, here we have the board, okay, which is actually blinking because we have the previous program in the in the in the board. Now let us try to can I fix it somewhere? Leave it next class, fixing next class, don't worry. Now I am going to upload this particular program, and let me show you one more thing. So let me just fix it because it will be much better if I fix it somewhere here. Let me just try. Yeah, let me just try this. uh my my board do not have that much of length. Let me check what is sticking here. My whole setup is changing, that's why. Anyway, let's check if I can fix it here. Let me check if my camera is visible. Yeah, here, right. So right, let me just if I try to zoom in, zoom. Okay, here is my board. Okay, some cables are still there. Let me move it now. Okay, so here is my board, and let me focus on the programming part. So here right now we have the program, and just first let us compile it. Right click and then rebuild all. I hope you can see my screen and my camera both, right?
Yes, sir.
Okay, so my program is compiled, and now I'll go to project options, and because I'm using the board, I'll go to debugger TI Stellaris. Okay, this is my ICDI. So done. So now I will upload the program. For that, I will go to download and debug. Click on that, and let us go through all the program line by line. I will avoid the disassembly right now. Rather, we will keep an eye on all the variables and all. So first go to the watch window. Here we have the watch window. I'll keep it somewhere here, and let me check. Yeah. So first of all, let us go to the port F. So here from the group, you go down and then find GPIO F. Okay. Then let us run the program line by line. Let me just arrange this. Okay. Okay. Let's go down. Okay. So first of all, RCGC GPIO. RCGC GPIO is not in the port F. We have to go to the system clock. So for go to system clock, either you can reach like this, or you can just type RCGC GPIO here in the find register. Click on that. Here you are the RCGC GPIO. So let us go down. Why this assembly is always appearing, I don't know. So I will keep it somewhere here, don't worry. Okay, so that they don't disturb. Okay. Now, the RCGC GPIO, we are entering 2. Okay, here. So you can see RCGCIO got the value in the 5th position. Let me reset it again if everything should be reset. Okay, stop it, reset. Okay, let me try again. Okay, sys is RCGC GPIO here. Right now it is 0000. So let us enter the value. Either you can go like this, one you left shifted by 5 positions, or you can just directly write the appropriate number there, okay, which we used in the last lecture. But this one is easier approach. Done. So now 20 is there. Here you could have written sysctl underscore rcgc gpi underscore r or equal to 020x. That was also correct. Now after that we can go to port F. So here, from here you can go to port F, which are our port for port of interest. Okay, so right now everything is 0. So let's go down. So dir register. So dir, where is dir? GPIO dir.
Second from the top.
Mm, this one. Okay, so you got 0e here. Why? Because you made first position, second position, and third position 1. Rest of the positions are 0. So you can right click here if needed. You can right click here, and for more easier interpretation, right click format and go to binary. With that, you it will be much more easier to understand why we are entering these numbers there. Okay, let me just resize the window if possible to make things more clear. Yeah, you here you can see 0 1 1 1. So these three 1 are 1 because you want the red LED, green LED, and blue LEDs, okay, direction output. We have declared that. Then we are going to declare it is digital enabled. So here you can see it is 000 by default. Now it is 0e. Again, all three are made digitally enabled. Here it is which visible. Now you can make the LED blue high. Okay, for that you are using array, and in the index third position you are entering 3. Okay, or you are entering 1 in that position. Okay, so let us go there, and you can see in the camera. Okay, here in the camera you can see the LED is blue. So by default the blue LED is on, and then we are going for the counter because the counter is too long. Okay, I am not going to run that part. Okay, and it is going to take lot of time, so I will stop it. Rather I will run it in a single go. So blue, and then like I said here, you can see now in the blue there is an LED red which is blinking. Okay, so this is how you can see the effect of the programming. So you can keep on changing the program according to your use, and for that today we learned how to simplify the program using first header file, second using the bitwise shifting operation to enter a particular one in that particular bit position. Apart from that, we also learned how to use bitwise ORing to just change certain bit positions without disturbing rest of the bit positions. Rest delay we have used in the previous class also, so there is no new thing about the delay here. Only thing is I have used counter as an array where we have defined two counters, counter number 0 and counter number 1. Okay, rest we have made the LED high here, and we have made the LED low here, and it keeps on repeating. If you have any doubts, then please ask the doubt in the next class. And with this, I am going to end the lecture. Please practice it, because rest of the things are not, it will not be clear until unless you keep on practicing from your own also. Okay.